Picture this. Right now, beneath a quiet Swiss countryside, scientists are recreating the first moments after the Big Bang. They're smashing particles together at nearly the speed of light, hunting for the invisible forces that hold our universe together. And here's the wildest part. They want to build something 3 times bigger. Welcome to the border between France and Switzerland, home to the most ambitious science experiment humanity has ever built. The Large Hadron Collider stretches 27 kilometers in a circle, 100 meters beneath farms and homes and businesses. Getting access to CERN, the world's premier physics laboratory, is incredibly rare. This is where thousands of the brightest minds on Earth gather to unravel the deepest mysteries of existence. Deep underground, behind reinforced doors, is where the magic happens, where particles collide inside massive detectors. These machines are absolutely enormous, towering several stories high. The engineering required is mind-blowing. Building them was like constructing a ship inside a bottle, except the bottle is an underground cavern and the ship weighs thousands of tons. Here's what happens inside this beast. Scientists take protons, particles so microscopically small that your mind can't really grasp it, and fire them in opposite directions through pipes kept colder and emptier than outer space. These pipes are only about the width of an orange, and powerful magnets squeeze the protons into a beam narrower than a human hair. The particle beam travels through a space as thin as a single strand of hair. But that's enormous compared to the protons themselves. Think about it this way. Take one strand of hair and imagine it's as wide as planet Earth. Now zoom way in until you can see a single cell inside that hair, which would be roughly the distance from Paris to Rome. Zoom in more. A protein in that cell would span 6 soccer fields. An atom in that protein would be the size of a school bus. The nucleus of that atom would be like a grain of rice. And the protons inside that nucleus? Grains of salt. That's the scale we're working with. A proton compared to hair is like a grain of salt compared to the entire Earth. And scientists are shooting these impossibly tiny things at each other from 27 kilometers away, expecting them to hit. How do you make grains of salt collide when you're firing them from opposite ends of a tunnel longer than a marathon? The answer is beautifully simple. Fire billions of them. Each beam contains 100 billion protons grouped into bunches, racing toward each other at 99.9999% the speed of light. When 2 bunches meet, 100 billion versus 100 billion, guess how many actually collide? About 60, that's it. 60 out of 200 billion. So they do it again and again and again, 30 million times every second, generating 1 billion collisions per second. But why? Why spend $5 billion in 30 years and involve thousands of people from over 100 countries to smash particles in an underground tunnel? The internet has theories. Some people think it's going to end the world, create black holes, open portals to other dimensions, or summon demons. That last one was literally a prank video that went viral. The truth is so much more incredible. When protons collide at these extreme speeds, something remarkable happens. Einstein taught us that energy and mass are interchangeable, and when these collisions release enormous amounts of energy, that energy can transform into matter. New particles pop into existence for just an instant before decaying into other particles that fly outward into sensors surrounding the collision point. Scientists analyze where these particles hit and work backward, like detectives at a crime scene, using incredibly complex physics to figure out what mystery particles existed at the moment of impact. This matters because those mystery particles are the fundamental building blocks of reality. Everything you see, everything you touch, everything that exists is made of elementary particles that behave according to rules we've spent decades discovering. Those rules are described by something called the Standard Model, an elegant mathematical framework that explains how our universe works at the most basic level. It predicts the existence of particles like electrons and photons, and it's been proven right again and again through experimentation. But before the Large Hadron Collider was built, the Standard Model predicted something that had never been observed: the Higgs boson, sensationally nicknamed the God particle. This wasn't just another particle to add to the list. The Higgs boson would prove the existence of an underlying field that gives other particles mass. It would help explain why stuff exists at all, why matter has weight and substance. That's a pretty big deal. The only problem was that creating a Higgs boson required more energy concentrated in one place than we'd ever achieved before. So they built the Large Hadron Collider. After years of construction and 2 more years of collecting data, scientists were finally confident enough to make an announcement. They'd done it. They'd reliably created the Higgs boson and detected it. The proof looked like a small bump on a graph. That's it. A bump. But that bump represented countless hours of work, billions of dollars, and confirmation of a fundamental truth about our universe that had previously been theoretical. Did discovering the Higgs boson immediately change your daily life? No. But when Isaac Newton discovered the laws of motion, he couldn't have imagined humans walking on the moon 3 centuries later. We discover the building blocks now so future generations can build with them in ways we can't possibly foresee. Already, work done at CERN has led to better cancer treatments, improved medical imaging, more efficient electric vehicles, and most famously, the World Wide Web. We don't know what comes next, but that's exactly why we keep pushing forward. The Large Hadron Collider has answered some questions, but it's opened up so many more. We know that dark matter makes up 27% of our universe. We can see its gravitational effects bending light around galaxies, but we have no idea what it actually is. We don't understand why there's more matter than antimatter. We can't reconcile quantum mechanics with gravity. These aren't small gaps in knowledge. They're enormous holes in our understanding of existence itself. That's why some scientists are now proposing the future circular collider, a machine 3 times larger than the current one, stretching 100 kilometers underground and costing an estimated $17 billion. Critics argue the Large Hadron Collider didn't deliver everything some hoped for, and there's no guarantee a bigger one will find what we're looking for. But others counter that we'll never know unless we try. And historically, pure research always produces unexpected breakthroughs. Here's what strikes me most. What we choose to spend our resources on reveals who we are as a species. If aliens visited Earth and examined what we've built, wouldn't you want them to find enormous monuments to knowledge? Wouldn't you want them to see that we're a species driven by curiosity? That we ache to understand our place in a universe that seems impossibly vast and complex? Yes, we're limited. Yes, we can only perceive a tiny slice of reality. But we try so incredibly hard to see beyond those limitations. The effort we put in today, the questions we ask, the experiments we run, they're building a foundation for a future we literally cannot imagine. That's worth celebrating. That's worth investing in. That's worth understanding. So back to my original question. What would you choose? A, B, or C? And after everything you've just learned, has your answer changed? Let me know in the comments below. And if you found this fascinating, smash that subscribe button and hit the bell icon so you never miss our next mind-blowing video. Trust me, what we're covering next is going to absolutely shock you.